Namaskar. Welcome to Prakash on Basics. I'm Prakash Zo. We started our discussion on electricity. And let me remind you that electricity, of course, is the prime source of energy that we have. So, in order to understand how electricity is used or applied, we need to know some of the basic ideas associated with electricity. A number of simple terms that we commonly use whenever we talk of electricity. And so, naturally, that is what I will first talk of today. We must know how electricity is produced and what are the terms associated with it. So let's begin. The first thing to realize is that electricity is because of current, voltage, and a opposition to this, which is known as resistance. So these are the three primary things we must understand first. But for current, there's something known as charge, and this charge is because of electrons. So electricity finally comes from electrons and the motion of electrons because of certain factors. Where does all this come from? That's right inside in the atoms. Remember what you studied in school some time back. There's a nucleus which is positive because of the protons, and there are some neutrons. And depending upon how many protons there are a number of electrons that keep going around. And these electrons form a number of shells around, so to say. And in the outermost shell, there could be certain number of electrons. These are typically known as valence electrons. And some of these electrons have a little more energy than necessary and are capable of movement from one place to another. And these are typically referred to as conduction electrons. To understand how all this works out, let's take a very simple common sense example. Suppose there is a very big family consisting of, let's say, about 20-25 ladies, each having 8 or 10 children. So all these children and all these ladies staying together have the children drifting around if they are slightly elder. And if they are very young or very small, they are permanently attached to their mothers. And if the electrons are similar within a metal, the electrons that are very small in energy content will be attached permanently to the nucleus. The others in the outermost region will be capable of drifting around. And so, all the children moving around in the house will have a collective attachment to everybody else within the family. But even if one child goes out, any mother around will drag the child back in again. There is a collective attachment now between this whole group of children drifting around and the mothers, aunties, uncles, and so many others that are around. The same thing happens for atoms. You have the nucleus and some of the orbits, and then a cloud of electrons, which is all negative. The rest of it obviously is positive. So there is an attractive force between this negative cloud and the positive charge centers that are there. This is typically what a metallic bond is. The whole system is neutral. The instant one of the electrons tries to go out, a negative goes out, so the remaining becomes positive and it drags the electron back again. So the whole system is pretty stable. But due to certain factors, it is possible that these electrons will begin to move around. And when they start moving around, the rate at which they move will decide on the amount of current that is produced. This is typically what happens in metals like copper and silver and iron and so forth. So there is what is typically referred to as a metallic bond with conduction electrons that are free. And so these are all good conductors of electricity. And if the number of children is very small, they are going to be permanently attached to the parents. And so there is no chance of these kids drifting around. And that's what happens in case of insulators, like wood and plastic and even air for that matter. All these are bad conductors of electricity because they have no free electrons to drift around. There are some, of course, which are intermediate between the two of them, and these are known as semiconductors. But that's not something for today. I'll come to semiconductors much later sometime. So we have good conductors and bad conductors. But there could be things like carbon, for example, typically carbon, which has many different forms. These are known as allotropes. So if you have graphite, it's a good conductor of electricity. And if you have diamond, you have one of the best insulators that is available. And then, how much charge does this electron have? The charge of the electron is the smallest negative unit that we know of, commonly talk of. Uh, minus 1.6 into 10 raised to minus 19 coulomb. Coulomb is the unit used for measurement of charge. That's the amount of charge on one electron. Very small number. 0.18 zeros, 1 6. And negative, of course. So many coulomb. So it's a extreme 0.0000000. Very small number. How did they measure it? That's very interesting. But that's a part of some beautiful experiments I will discuss much later. Not today. Just this is the amount of charge, and the proton obviously which is within the nucleus has exactly opposite, that means positive, same amount of charge. Now when this charge begins to move around, the rate at which this charge moves results into what is typically known as electric current. But why should they move? So for movement, there is another factor that is equally important, and that is what is known as electrostatic force, a law that was put forward by a person called Coulomb and so forth. Let's not bother about that. What it says is that if there are two positive charges, they'll repel each other. If there are two negative charges, they will repel each other. And if there is a positive and negative charge, they will attract each other. And the more the amount of charge you have, the more is the attraction. And if you double the distance, the force will become 1/4. So it is inversely proportional to the square of the distance. Realizing that far further they are, it becomes less. Closer they are, the force becomes more, and so forth. It's a common sense issue. Now, as I said, these electrons can be moved around, and the movement or a transfer of, let's say I take a system in which one electron is removed. So the remaining part becomes positive. Two electrons are removed, it becomes two charges, and so forth. Because of it, it gains a certain amount of ability to attract other electrons. How far can it attract? That range is referred to as the field. In this case, electric field. Same way, there could be magnetic field. The distance up to which a magnet can attract a nail is known as its magnetic field. Same way, there could be light intensity. If there is a light source at a particular point, the distance up to which the light's effect can be felt would be measured in terms of the intensity of light at that particular point. So there would be electric field intensity, magnetic field intensity, light intensity, and so many things. That's what gravitational intensity and so on. So that's the distance up to which the effect will be felt. If I'm today sitting in Atlanta, a different place than the normal place where I work, and if I switch on a light here, the light is not going to fall at home in Pune, because the intensity of light by the time it reaches there will be blocked and so forth. Neither can I expect a magnet to be kept here and attract a nail even 10 feet away. So the intensity of the magnetic field will decrease. So that's what happens to all charges and everything around. Now, there's one more factor that happens along with this, and that is that the level of removal of these charges causes a change in what is known as the potential, or the amount of energy per unit charge that is possibly stored in the system. And this potential is the one that causes charges to begin to move. This potential is measured in terms of what is known as volt. It depends upon the way in which the charges are stored. To understand this, let's take a very simple example. Suppose I have, say, about a liter of water, and I pour it in a bucket. The level rises maybe about so much. Instead of that, if I take a certain amount of charge and pour it or store it in a certain system, its potential will rise up to a certain level. If I take the same 1 liter of water and put it in a cylinder, now the charge is going to be, rather the water is going to be stored in such a manner that its level is much higher. Same thing would happen to charges also. And so if the same amount of charge is stored in a system where the storage pattern is different, then the potential would rise much higher. And this potential is measured in terms of what is typically referred to as volt. So the same 1 liter of water would flatten out, so the capacity of that container will be much greater. And the same 1 liter of water poured in a vertical cylinder would raise its level much higher. And so the capacity of that cylinder is going to be much lower than the bucket that we talk of. Same thing happens to charges. And this storage capacity in terms of charges is referred to as capacitance. And these are a number of small devices that are used in electronic circuits, capacitors as they are known as. A typical one is associated with the electric fan that you have. And when it fails, the fan starts making a noise, wow, 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 and so forth. So that's a capacitor. Now, it is this potential which is at a particular level. There could be another object at a different potential. This could be at 10 volts and this could be at 2 volts. And so there is a certain potential difference. And this is PD, the potential difference that we talk of. Many of us know it as, if you are in India, it could be 220 volts. If you are in US, it could be 110 volts and so forth. That is the potential difference that we talk of. The voltage typically talked of. And it is this level difference that causes things to move. What is going to move is obviously the electrons. And reuse a little bit of common sense. If they are at same level, the electrons won't move. And more the level difference, greater is the rate at which the electrons will move or flow from one point to another. And their flow is going to result into a current. So the amount of current that flows through a particular conductor will depend upon how much is the potential difference. And that's probably one of the most important laws for electricity. You must have heard of this, which is known as the Ohm's law. The amount of current that flows through a particular conductor is directly proportional to the amount of potential difference that is applied between the two ends of the conductor, provided there are no other changes that take place in the system. That's the situation. So, the more the potential difference I apply, the more is the amount of current that flows through. So, what is current finally then? It is the amount of charge that will flow through per unit time. So if I have 1 coulomb of charge flowing through a particular conductor in 1 second, I would say that the current is 1 ampere. And if it is 1,000th of it, I would say it is 1 milliampere. And if it is still 1,000th of it, I would call it a microampere. And if the voltage is 1 volt or 1.5 volt as it is in a battery, I would refer to it in volts. Or if it is to be used in something like a TV, it would be in kilovolts, which is thousands of volts. And it could be much higher in megavolts and so forth. And the lightning that falls in the sky is going to be in megavolts and so forth. So there is different voltage, there is different amount of current, and there is a conductor through which all this flows. That brings us to one more simple term that is often talked of in electricity, and that is resistance. The word resistance is obvious. It is the opposition to the flow of current through a conductor. It's a different way to look at things that must be understood. Suppose there are 100 people who want to cross to the other side, and there is a door in between. If all 100 can go through, no problem. But if the door allows only 10 people to go through because it's small, then it means that it is providing resistance or opposition to the 90 that cannot get through. So only 10, 10, 10, 10 will go across each time. If the door is still smaller, the opposition would be still more, and only about 2 or 3 would be able to go through every time. So its resistance to the flow of people through is much more. That's exactly what happens to currents. But I could look at the same problem from a slightly different point of view. I could say that the door allows 10 people to go through, or 20 people to go through, or 30 people to go through. In this case, I would be talking of it as conducting or permitting people to go through. And if there is a situation where all these 100 can go through, there is no opposition at all. So there is no resistance. And that typically is what we nowadays hear of as superconductors. There's no opposition to flow of current. And any even 1 volt of potential difference could result into maximum amount of current that can possibly flow through available. That's how. So we have resistance as the opposition to the flow of current. So the three major things: voltage, current, resistance. Resistance is like the door that I talked of. It's like a road. If the road is broad, more cars can flow across. So if the metal is broad and thick and has a great cross section area, its resistance will be pretty small. And if it's very long, thin, then it's like a thin road stretching across a very large distance, and the amount of vehicles that can get across is very small. So naturally, the amount of current would be small in such conductors. And so a resistance is more if the length is more, and a resistance is less if the width is more. There's one more thing. The vehicles flowing through will depend upon the type of road conditions. So if there are potholes and other stuff, the vehicles going across will be very small in number. So naturally, the opposition will be more. And if it's a smooth paved road, it's very smooth, the number of vehicles going across will be more. And that's what happens in different metals. So if we have a metal like copper, the flow path is very smooth and more amount of electrons can get across. And if there is a rough road, even iron, for example, there would be a lot of hurdles, and so the amount of electrons going through uh, would become much less. And we humans have learned how to change this value. So we could have a mixture of two metals like nickel and chromium, resulting into nichrome. And this nichrome is going to oppose the flow of current to a very large extent, and it's going to result into a lot of moving around. That's what results into the large amount of heat. So all properties are associated with how electrons flow through substances. And that then is one major step of understanding voltage, current, resistance. And if you take the amount of voltage and multiply it by the amount of current, what we get is what is typically referred to as the power in the system. And that is the one that we measure in terms of watts or watts, as some people pronounce it. And it could be megawatts or kilowatts and so forth. So when I talk of uh, a electric iron, it could be in a few kilowatts. And if you have electric diesel electric train, it could be in megawatts and so forth. And the power produced at a particular point could be much higher, in gigawatts and so forth. So this is how electric power is talked of. Then what about the way in which these electrons flow? There are 2 3 possibilities, and that results typically into the type of currents that are produced. One is because of the motion of the electrons themselves, and this is known as electric current. But if I take a particular substance and remove one electron, the remaining part is referred to as a positive unit, which is typically known as an ion. And it is possible that because of this voltage difference, these ions would also move, and that would result, and their flow would result into ionic current. So electron flow takes place in case of metals, but if it's a electrolyte or a liquid, such as a little bit of salt added to water, then it is going to be in terms of the sodium and chlorine ions that move, and so that will be an ionic current. And when a lightning strikes The air in between is ionized and converted into ions, and the electricity starts flowing down. So that is a typical discharge of electricity through air, which is the lightning that we talk of. And remember, all the electric batteries that we use, whether it is the earlier ones or even today's lithium ion batteries, all of them produce electricity because of the flow of these ions within the batteries, resulting into an electron flow outside through metals. So there could be uh, current because of electrons, or there could be current due to ions. And there is one more aspect there, and that is, what is the type of electricity that we look around. And that type of electricity could be classified into three different types. One is static electricity. The second is the one that results into direct current. And the third is the one that we use commonly, which is the uh, alternating current. So there are three different types of electricity that we know of. Static electricity is typically the ones in which, when two things rub across each other, some of the electrons get transferred, and one becomes positive and the second one becomes negative, and the potential starts rising. And if the potential rise is very large, it can result into attraction. And typically, as small children, many of us have tried. You rub a balloon on your hair and stick it to something, or you rub a comb and have small pieces of paper jumping up and down. That is all because of static electricity. And the lightning is because the mountains rub across, sorry, the clouds rub across each other and transfer electrons. And the transfer of electrons results into potential difference between them, and this builds up to a very large extent. That is the one that causes lightning bolts to strike down. You could have fur that is used, which is rubbed across backlight, or some material, acrylic or something of this sort, and all these charges would start accumulating. So the possibility of developing a very large amount of voltage is possible here also. A lightning typically could result into 10,000 kilovolts per centimeter approximately, is the amount of voltage required for a lightning to take place. When sparking takes place, the same thing could happen. Uh, there were certain machines like Wimshurst's machine and all that were developed for all these static electricity. But static electricity is pretty important. One of the most common examples that we know of is the attraction into very small carbon particles on a charged sheet of paper would result into the Xerox copies that we know of. So the paint adheres, or the particles adhere to a particular surface because of the electrostatic force that is applied initially. And when cars are painted in factories, etc., what they do is they make the sprayed particles of one charge, and the vehicle is made of the other charge, so that all the paint, rather than scattering around in spray painting, would fall on the object itself, and there would be very little wastage. And many of you all must have heard of smoke precipitators. They are all based on static electricity. And we have ions that are sprayed on clouds, which result into rainfall. All these are associated with the processes involving static electricity. All sparking that takes place is because of static electricity. And all the batteries that we know of, all the cells that I talked of, and the batteries, they all produce current flowing only in one direction. And that typically is direct current. So a DC current is direct current where the current flows only in one direction. There's one hitch that must always be remembered. Because of the initial decisions that were taken when electricity was being studied, electrons are taken as negative. And so what we call as positive is the one towards which the electrons flow, which is negative. So the conventional current flows from positive to negative. That's something that happened many years ago, and it has remained the same. So we have always treated the electrons as negative and protons as positive. And the flow of electrons is the major aspect, and the direction of flow of actual current is opposite to the direction of flow of electrons. Let's not bother about electrons every time. Then we come to what is known as AC, that is alternating current. I just had mentioned last time that there are generators which produce electricity, and the whole thing spins around. A coil that spins in a magnetic field produces an alternating current. But if you think of the coil that is turning like this, the lines that it cuts of the magnetic field will depend upon the angle at which it is. And it changes in a certain pattern. So the value rises up, comes back to zero, then rises in the opposite direction and comes back to zero. This is typically a mathematical process which is referred to as a sine wave. So the voltage that is generated will also vary in the same manner. And so the current it produces is also in the same manner. So we have what is known as alternating current, and you have an alternating voltage. And depending upon how many times you turn per second decides on the number of times this would oscillate. And the generators are designed and made in specific patterns. So in India, the frequency is 50 hertz, that is 50 rotations per second. And in the US, it is 60 hertz, which is 60 times the AC cycle would fluctuate per second. In most of the cases, this 50 hertz and 60 hertz hardly makes any difference. But the level difference is much different. In India, typically we have a voltage difference of 220 volts, whereas in the US, you have a potential difference of 110 volts. I'll go into details of this when I start talking of household electricity and its applications. Um, and then once you have an alternating current, what typically happens is it also produces a magnetic field around it. And using this varying magnetic field, it is possible to make a number of devices that help us. Transformers, for example, typical, the ones which help to bring the electricity all the way up to your homes. You have what are known as step-up transformers, which can increase the voltage. And you have step-down transformers, which reduce the voltage. So when you are using a TV, the voltage that is either 110 or 220 has to be boosted up to about 2000 or more, in which case you have a step-up transformer inside. And when you are using a charger, for example, or a battery eliminator, that 220 volt, if you give it to your mobile, it will just have smoke coming out of it. So it's not going to work. So you need to do two things. One, you need to reduce it down. And for that, what you typically use is a transformer, which reduces the 220 or 110 to 5 or 6 volts. And that's written on your chargers. There's one more issue. The electricity that we have at home is AC, and the battery inside your mobile or a camera is direct current. So the device must not only reduce the voltage, but you must also change it over from AC to DC. And that exactly is what is done when you are using a battery eliminator or a charger, which reduces 110 AC to 5 volt DC. And that's how the process works. So all these electric devices that we look around us are typically the ones that use either AC and, if required, DC, and it is possible to convert one to the other. You have inverters which convert DC into alternating current, and you have the gensets that are typically used. They are just nothing but petrol driven generators that produce alternating current whenever electricity or power fails. And you have a replaced power from DC to directly going into AC, or you have an AC generator itself. So there are a number of typical devices that are around us. They all work on electricity. They all work beautifully. We'll talk of many of these devices as time comes. But the terminologies that I mentioned just now are the ones that we must know: voltage, current, power, AC, DC, static electricity, and so forth. Once these terminologies and how all this current flows is clear in your mind, we can then look into the number of different applications that are our life around. Even our body, as I said, works on electricity. That, of course, is DC. How it's DC and how it works, I'll come to sometime. If you have liked whatever I have said, if you have appreciated what I have said, tell this information, pass this information to your friends. Let them also understand the beauty of what electricity is. And let's understand electricity a lot better. Please like and subscribe to this channel. Tell your friends about it. Next time, we'll go into how a number of devices that are used at home which work on electricity function. Till we meet again, Namaskar.